Okay, so before we start, some words about Mr. Josef Janisch. He has quite a lot of experience, more than 35 years in the semiconductor industry.
Look at me.
AMS, Austria Microsystems in Unterbremstetten. We worked together for a long time. And there he spent a long time also in the United States, starting from 2000, and supporting customers in Canada and also in South America as a field application engineer. And in 2010, he started working as a product manager for ZMD, Zentrum Mikroelektronik Dresden, in Germany, where he started a new product line focusing on contactless position sensing ICs. Then opened an office in Ilz, which is still the office, but the company has changed.
Yes,
from
twice.
ZMD to integrated device technologies by ZMD during this days. And the last acquisition was from Renesas. And now Josef is part of the big corporation in Renesas and heading the application field application engineering and research innovation activities in the location of Ilz. Josef, thank you very much for coming.
My pleasure. Thanks, Bernd.
Looking at the technology behind, in fact, all we need are three basic ingredients. And you have all heard about them. The first one being the induction in a wire loop. Imagine you have a magnetic field, you have a loop of wires. That's what Henry and Ørsted have described a long time ago. Number one. The second one, the classic transformer, primary coil, secondary coil. In our case, as we are dealing with printed coils, an air transformer, so an iron-less transformer, which doesn't really make a difference. But that's the second principle we need. And the third ingredient is eddy currents. Why eddy currents? These sensors operate in the 2 to 6 megahertz range. That's an open frequency band between medium wave and short wave radio bands. There's this one band, about 2 to 6 megahertz, where pretty much all of these inductive sensors are operating. And at this frequency, you can utilize the effect of eddy currents. We're all familiar with the inductive cooker. So you have an RF field, you have a metallic base, and the metallic base then, let's say, sucks in the energy from the RF source and converts it into heat. But essentially, of course, we're not talking about heat here. We are talking about the dissipation of energy away from the source. So now let's mix all this together, and that's what we come up with. That's pretty much what you have in your hands, and you see some other designs there as well. They're all based on the same principle. So what we need at first is a PCB, a printed circuit board. It can be as simple as a 2-layer FR4 material, nothing special at all here. Classic PCBs, and depending on the application, these are fairly cheap. The second one, naturally, the chip and some external components. And the coils. We will spend a great deal of time about how these coils are working. So how essentially we are converting the sensing of a position of a metallic target into an actual digital or analog output. We'll talk about that. In our case, we are talking about a single transmitter coil. Think about the primary part of the transformer, and we have 2 receiver coils. Why 2 we will see in the following slides. But essentially 1 transmitter, 2 receiver coils, a metallic target, and by metallic, anything that conducts current, copper, aluminum, iron, qualifies as a target. There's not any special requirement on that. The thickness as such is also not so critical. In these frequencies, we are talking about a depth of how far the eddy currents are, the currents are going, a few microns. So whether it's 20 micron or the standard layer, 35 microns of a PCB, that's about good enough for a target. You don't gain much if you make it any thicker, but on the other hand, of course, you can already use an existing shaft and you cut these shapes into the shaft. That would qualify as well. So it doesn't have to be a PCB, it can also be some shaped metal to qualify as a target. Now, let's do step by step. We start with the generation of the RF field. Again, we talked about 2 to 6 megahertz range. Classical, that's an LC tank, an LC oscillator, which uses, let's say, utilizes the best of the energy. So we don't really need that much. We talk about a few milliamps of current into the transmitter coil is good enough to operate it. And naturally, since this is a printed coil, the field that we are generating is in and out of the plane. So we are talking about the field in this direction, right? So that's the transmitted coil. So in plane, out of the plane, depending on the polarity of the RF field. And that's typically a sinusoidal waveform, not a rectangular one, but that's purely due to the fundamentals. You don't want too many, the harmonics, you don't want too many harmonics in the emitted spectrum. So that's why we use clean, let's say, sinusoidal signals here. Secondly, and this is where the air transformer comes in, where there is a transmitter, there needs to be a receiver. Let's start with a simple shape, classical air transformer. Now you will argue, we have here the transmitted waveform and the received waveform exactly 360 degree in phase or zero phase. That's not, as we know, exactly true. There is some phase shift between primary and secondary in these transformers. But for the sake of the following slides, we can safely assume that this can be in phase. There are ways to correct the phase shift, but it's not something we need to talk about here. For the ease of understanding, we assume that the primary and the secondary can be in phase. Now, as the first thing, remember right around 6 megahertz on the transmitter. Same phase is then coupled to the receiver. And now let's put a metallic target. We call it target. This is this metallic piece, the one you have also on the back of your beer keg. This beer plate here. That's a classic target. And if we place this target, this is now where the eddy currents come into play. As I move a target over this, call it air transformer, some of the energy, as we know, is now dissipated inside the target. And this dissipated energy is then missing here on the receive side. So I already have some form of position sensor because I can sense by checking the secondary signal, I could theoretically sense the presence of this target. As a real position sensor, it wouldn't qualify because it would not be able to distinguish whether this, let's assume this is our coil, this is our target, whether it moves in this direction or in that direction or this direction, it wouldn't be able to tell the difference. So that's a first step into an inductive position sensor, but certainly not good enough. So we need to do something else. The first thing we do now is we are winding what we just saw earlier, this receiver coil. Now we are twisting it and make it into an H shape. So we are twisting it like this, meaning that one half of it is clockwise, the second half of it is counterclockwise. Compared to the transmitter coil, it means one half of it is in phase with the winding direction, whereas the other one is out of phase, the opposite phase. What happens now if I add a metallic target? Now watch the polarity on the output. Depending on which part it covers, the output is now either in phase or out of phase. So we already have a second distinction now. We can sense the movement in the horizontal direction. But still, it would not be able to tell whether it's going in this direction towards zero, and then in the opposite side, or it's going in this direction towards zero. So still, it's not sufficient enough. There's more to do. In this slide, we'll see, and it's good to understand now why it would make sense to look at the whole picture first before we go back to the design of the coils. How can I really get an output signal that's proportional to the position? And this goes back to the older radio days, amplitude modulated demodulation. I have a transmitter signal. I have my coil structures. And then I need to do a demodulation. And after demodulation and low-pass filtering, I get a DC signal, which is proportional to A, the polarity of the received signal, positive or negative, and the strength of the received signal. The larger the strength, the larger the level of my output. So polarity means in phase or out of phase. Strength of the coil of the output means amount of field that's being induced in the secondary coil. Demodulation, you're familiar with maybe the Gilbert cell, a classical four-quadrant demodulator. Another method that qualifies as a synchronous demodulation. So you invert or not invert the secondary depending on the polarity of the transmitter, gets the same output after low-pass filtering. You get a DC signal that's proportional to your position. Again here, demodulation. I'm sure you're familiar about this. Let's assume now the transmitter level stays the same, and we are changing only the amplitude of the received signal, which is essentially what we're doing is we're moving the target, which does change then the received signal. And why it is so, I'm moving from the sideband, so from the RF by demodulation and low-pass filtering, we are moving into the baseband, into the DC to a few kilohertz range. These sensors, by the way, are operating, because I mentioned a few kilohertz, in our case, we talk about maximum 10 kilohertz. 10 kilohertz, if you translate this into rotation, 10,000, let's say, periods per second is about 600,000 revolutions per minute. That's quite a high speed, and that's good enough. We don't really need more than that. Why does anyone ever need 600,000 RPM? We'll see about this later. If you have a multi-periodic one, let's say this would be a 10-periodic target, the sensor actually sees 10 times the speed of the mechanical rotation. So that's why 600,000 RPM is for a single periodic sensor, but typically in these brushless motors, we have multi-periodic designs. Let's say for a 10-pole design, it would be 60,000. So that's where the high speed comes from. Let's do a quick look at coil geometries. I have the freedom as the designer of this PCB, I have the freedom to pick what kind of shape do I want for the receive coil. Should it be square, sinusoidal, something like that? And likewise, I can modify the shape of the target. We can do both, but in order not to overdo our presentation, let's assume we are using classic square or rectangular targets, and we are modifying in this case only the shape of the printed coil. So if I have a square coil and a square target, the output would be some kind of linear or triangular output. If I have a sinusoidal coil generates a cosine response. Again, the x-axis here is the position, the y-axis is the signal that I get at this position. So sinusoidal coils, cosine shape output, and naturally likewise a cosine shaped coil generates a sine output. And these two are the ones that I need to move on. Now imagine we put both of them together. I have a 2-layer PCB, so I can put vias up and down. So this shape can be easily created on a double-sided PCB. No big deal. I have a transmitter coil generating my magnetic field. Well, one thing that's also worth saying here, we are assuming in these simple designs that the field, the transmitted field that we're generating is homogeneous over the area of the receive coils, which is not necessarily the case. So to be precise, in order to, let's say, increase the accuracy, there is some twisting needed on the receiver coils to compensate for the non-homogeneous shape of the field generated by the transmitter. But that depends on a big deal on the type of coil designer. That's a pure application type of design. It's nothing to do with the chip itself. The chip doesn't really care what is connected to it. But we have some means of linearizing and compensating those. So first thing, we generate a transmitted field. We have 2 receiver coils, a sine-shaped and a cosine-shaped coil. Depending on the position, so we are introducing a voltage in the receiver coils. And as we move the target now, we are getting a sine and a cosine shaped output. Why are we not seeing the full 360 degrees? Because that's the part that's missing as the target moves over the sensor. So we have the length of the sensor, which would be 360 degrees, minus the area that's already covered by this target. So we can only move, let's say, the length of the coil minus the length of the target. That's why this is not a full 360 degree shape. But we'll see in one of the next slides how you can also get this one to the full 360 degrees. So you get the idea. The point here, and this is the important part, where we can cut out the influence of the vertical distance, is the ratiometry. Instead of measuring a voltage, a sine or a cosine shaped voltage, that's clearly dependent on the air gap between the target and the coils, I'm measuring the ratio of the two. That's where I get rid of, mathematically spoken at least, how I get rid of the influence of the air gap. And that's important in practice. So let's wrap up. We have the horizontal, and we're assuming now a rotating design, but it of course would apply to a linear as well. We have a sine and a cosine shaped. So the first one being the amplitude of the signal multiplied by the sine of alpha being the angle. And the second one, amplitude multiplied by the cosine of the angle. In our considerations, and we'll talk about this in one of the next slides, we need to assume now, and that's important, that these two signals have the same amplitude and are not shifted with an offset around the zero axis. So they are symmetrical across the zero and they are matching in amplitude. If that's not the case, you need to do something about it to make it so, in order to apply this simplified formula, how to get from here to the position. So the first thing is we divide sine by cosine. And again, we have the two signals, amplitude, peak amplitude multiplied by the sine of the angle, divided by peak amplitude, divided by the cosine of the angle. Now you can quickly see division of the amplitude. The first thing that cancels is the amplitude. Meaning, what I'm canceling, in fact, is the effect of the vertical distance. Because the farther I move the target away from the coil, the smaller will be my signal. But if that's the case for both of them, sine and cosine, the cancellation is still true. Whether this is 1 volt or half a volt or 100 millivolt, 100 divided by 100 is 1. So that's an important part, that I can decrease the influence of the vertical distance. And the next thing we know is sine divided by cosine. We learned it is the tangent of the angle. So consequently, the arctangent of this expression here, all that remains is the angle alpha. That's as simple as that. And that's what we are doing. Not just we, that's how all these sensors are working. But it soak a little bit, or is this so far clear? I think we get the idea, right? What it does. So and this is called, by the way, aquatic transformation. We'll speak about this in the next slide. Now let's use two use cases. I have a red and a blue line, a solid and a dashed one. Red and blue we know sine and cosine, the two geometrical shapes of the coils. And the dashed line being a small air gap with a large signal as the solid line, the dashed line a weaker signal with a larger air gap. If I now convert this rectangular coordinates into polar coordinates with the cosine in the horizontal axis and the sine in the vertical axis, I get my classic what is called the unit circle. And as I rotate, you see all that changes. If I change now the air gap, all that's changing is the length of the vector, but not the angle itself. So the air gap changes the length of the vector, but not the angle. Why am I saying this? It also has a benefit to not only look at the angle, but also at the length of the vector. In other words, square root of sine square plus cosine square. Why? Because in this case, I can do a sort of a safety check. If I have no target at all, this vector becomes zero. So I can detect not only the angle position, but I can also detect if there's a missing target, or if for some reason the air gap is changing and I'm getting weaker and weaker signal, I could use an automatic gain control to increase the receive gain and bring the length of this vector into a reasonable band between minimum and maximum range, so that it works in the less noisy signal. It has a less noisy signal. Mathematically spoken, if you take the arctangent, it's not a straight line. It's actually this sawtooth shaped line. So you need to do another calculation depending on the quadrant that you are. First quadrant 0 to 90 degrees, second and third quadrant 90 to 270, or fourth quadrant 270 to 360. You need to add 180 or 360 to the arctangent in order to get a straight line. Why do I know which quadrant I'm in? First, second, third, fourth, is simply by looking at the polarity of the signal. First quadrant, sine is positive, cosine is positive. Second quadrant, sine is positive, cosine is negative, and so on and so forth. The polarity of the signal determines the quadrant. And then once I know the quadrant, I add 180 or 360, and I get my 0 to 160 degree straight line of the angle. Practical examples, there are some here. Feel free to, after the presentation, come here and take a look. So it's all sorts of shapes, from arc-shaped to rotary-shaped. You saw the maneuvers, that's a linear one, and they can be as even bigger than that. It's really limited just by the length of the PCB. So the chip actually doesn't really care whether it's a linear or rotary or arc, whatever. All the chip sees is some sine and cosine, and it converts it into an output. And now again, let's take a look at this from the electrical point of view. Remember, we had this one before. That's the classic one, let's say. The linear sensor, one periodic, one target. I get an output of a sine and a cosine, which is 360 degrees minus the length of the target. How to get from here to a full 360 degrees is by simply adding a second one. So if the target moves on the right hand out of the coil, the second one comes in on the left side, and that's how you get the full and utilize the full 360 degrees. It really depends on the application. Do I have space for a second target? Yes or no? If I have, it would be beneficial to add another one so you can utilize the full 360 degrees. Same thing would happen if I just take this design and bend it slightly into an arc shape. For the sensor, it's no difference. It's just a little different how the target has to be shaped and how the coils need to be shaped, but essentially I'm getting the same thing. And now let's take the bull by the horn. We take both ends and put them together like a donut. And as you can imagine, now we have a full 360-degree sensor. There's no limitation, because if one end of the target moves out one way, the other opposite one comes in on the opposite side. So this type of design is always 360 degrees. There are cases where I don't necessarily need 360 degrees. Let's say I want to measure a position which is 180 degrees. A valve, for example, controlling the flow of water, gas, whatever. I can make a design like this. And I already doubled my resolution, because our one mechanical turn, I get 2 electrical periods. And so on and so forth. This is the one you have on this. So that's a classical. That's a 4-periodic design, 4 times 90 degrees, but you have the full resolution over 90 degrees. Of course, you would not know whether you are here or here. The signal repeats itself. So this kind of application is only absolute from within 90 degrees. What do I mean by saying absolute? We didn't really talk about this yet, but it's important to know that these inductive sensors are absolute sensors, meaning when I turn them on, it knows immediately where the target is. You don't have to go to a home position first, reset, and then start counting from there. You change the target, you turn it off, you turn it on, it gives it a new position. There's no homing needed. These are absolute sensors. Of course, absolute only in the sense of absolute within one period. In order to make this a high resolution absolute sensor, what you could do is you take a second one with 1 period, and then you combine the 2. The second one tells you which of the 4 quadrants you are in, the 1 periodic one, and then you just calculate the position from the first one. So you have 4 times the resolution in this kind of design. That's an implementation in a real sensor. That's a block diagram of one of the sensors that Renesas is selling that has been developed here in Ilz. You see the classical ones that we already had. We have the sine and the... well, let's start with the oscillator generating a radial field. Then we have the analog front end up here doing the offset and gain adjustment. And this is what I mentioned earlier. Remember what we said about sine divided by cosine, arctangent, and so on and so forth. It only works if sine and cosine have the same amplitude and there is no offset between them. And that's what this first stage does. You correct for the offset and amplitude mismatch to have clean signals, and then you can apply later on in the output the arctangent or the quadic function. Yeah, the rest is demodulation. Could be a Gerber, could be a Gilbert cell, could be a synchronous rectifier, demodulation, low-pass filtering, and then it's put to the outputs. That. Of course, there's a lot of safety to be involved as well. This was more about the principle as such, but in a real application, especially when it goes to automotive, you have a big deal of safety involved. FUSA, functional safety. You need to perform all these checks. Is there a broken coil? Is the voltage in the right range? Is the receive signal too weak, too small? Is the oscillator operating in the right frequency? There are countless measurements in parallel in the background to verify that this sensor operates safely. That's what we call FUSA, and this really depends on the safety level of the final application where it's been used. But this is just a side note. It doesn't really change the principle as such, but it's additional checks that need to be required in order to sell it, for example, in safety-critical automotive applications. Quick word about resolution accuracy. It's often being confused, especially by our customers. A high resolution sensor is not necessarily also an accurate one, and vice versa. So this shows that, let's say, the ideal line is the 45-degree line, but you can have a very fine resolution, but if it's not matching the 45 degrees, it's not accurate. And likewise, if you have the one here on the top right is the perfect one, but just to depict here how to not confuse resolution with accuracy. They are somewhat related, but not necessarily. A high resolution is by default also a high accuracy sensor. Quick recap of the pros and cons of inductive sensors. That's more of a marketing slide, but I don't spare you with this one either. You see, it's the main adoption for this kind of sensors is to replace, on one hand, existing magnetic sensors, because you don't need a magnet. All you need is a piece of metal. You can imagine that this is a lot cheaper, and you're not depending on these rare earth materials, samarium, neodymium, and such. Just a piece of copper is good enough. One thing where we see a good market for our products is the replacement of so-called brushless resolvers. A resolver is similar to an electric motor, but just the opposite. The resolver has a primary and a secondary coil, rather a primary and two secondary coils, very similar to what we have here, but it has the size of an electric motor, more or less. Resolvers are often used in ships, in airplanes, in heavy industries, even in cars. A lot are still in use. And these small, you can see the form factor is a lot less, the weight is a lot less. In fact, just as an example, I had one customer in automotive telling me that the main reason, and this was going into an electric vehicle, the main reason why they are replacing their brushless resolvers with our technology is not the performance, price, yes, but the main reason was the weight. He said, if I can take out my 10 resolvers that I have, that's at least 10 kilos of weight that I can take off the car, which helps me to extend my range, let's say, in this sense. And it's easy to do as well. Speaking about temperature, by the way, these chips are qualified from minus 40 degrees up to 160 degrees ambient. It's quite a lot, but think about electric motors, very compact ones. They can get pretty hot inside. But since we are not immune to the stray fields, we can move these sensors quite close inside the motor, and we get a small form factor. You know, the overall outline of the motor becomes a lot smaller, because, like in the old days, where the sensor is screwed to the end of the shaft, this is right inside the motor now, and the whole motor the assembly becomes a lot more compact. The other thing is, since I'm, as the designer of the PCB, I have the full freedom, how to design the coils, how to shape them, what is the best way for the coil. I don't need to buy a different chip if I want to use it for this or that application. It's the same chip. It's just me changing the shape of the coil, and I can reuse the same chip in a completely different application. So I have, as the user, the full freedom to design the coils to whatever shapes and forms I need. The other thing is, it's an advantage and a disadvantage at the same time. Compared to magnetic sensors, no doubt these are quite large. Of course, we have some as small as this one, but that's a typical application for a traction motor for an electric vehicle. You know, the ones that sit right at the axis of the car. They are big, no doubt. But at the same time, the bigger the coil, the more room I have for misalignment. So as these designs get bigger and bigger, my tolerance level for X, Y, and tilt misalignment gets better and better, because it's the relation of the voltage change that the chip sees. But if these are big, I have more freedom to move in the horizontal misalignment direction. there are downsides, of course. I mean, that's why magnetic sensors will still continue to exist. That's why brushless resolvers will continue to exist, which is there is some space required. If this space is not good enough, then this sensor is not good enough for you. If you need even tinier space, then I'm afraid we cannot really help. Then magnetic sensor is probably the better solution. And the thing is, we spoke about this great insensitivity to magnetic stray fields, because we are not using permanent magnets, we're using piece of metal. We're not sensitive to magnetic fields. Nice. However, keep in mind, we are sensing the movement of a piece of metal. So if you have another piece of metal running underneath, that won't work either. So you have to make sure that what is moving is the target that you're interested in. Or in our case, typically what we are doing is, if you have some other piece of metal running underneath this chip, then simply put a shield inside between them. Then you're good. How far away does this sensor need to be? Imagine this table would be a metallic case that we are putting our sensor in. How close can I put it before it gets too much and before the base plate is eating up all the energy and not the target? We are talking 1-2 millimeters, so it's not a big deal. Rule of thumb here is that this target should be closer to the PCB than as any other metal underneath it. It doesn't have to be centimeters away, a few millimeters is good enough. And ideally, it should be homogeneous and a complete full piece of metal, and you have shielded everything. So you have seen those coil designs, and you would ask yourself, how on earth would I be able to ever design such a coil, and even with this high precision? Well, probably you can't. We also had to learn it the hard way. But what we and other competitors are offering for such kind of applications, we are offering design tools to generate those coils for you. So you give it the shape. Let's say I want a circular one with 40 millimeters outer diameter, 30 millimeters inner diameter. I want 4 periods per rotation, and the tool generates it for you. Also, we have a so-called coil optimization tool. So after this has been generated, typically this is done by our customers using a tool that we provide. And some, let's say, higher volume ones, depending, of course, we need to rank the support by the size of the project, to be straight. We also have ways to simulate these designs. This is running in the cloud. And it's optimizing, then twisting and turning the coils until they are perfect. And this way we can achieve accuracies typically 0.1 degree electrical. And that's in the range of an optical encoder. So there's no downside as far as that goes. But it's all about the shape of the coil, and of course some correction inside the chip, what we said earlier, offset, amplitude matching, and things like that. So no worries, there are design tools available to design these coils, and once you have this, all you need to put it, copy and paste it into a Gerber, the Gerber files into your PCB design tool, and then manufacture it. We actually also, for our larger projects, we are doing, and that's also what the ILS location is doing, we are doing these complete designs, not just trying to sell the chip, but we're doing complete designs, including PCB, including evaluating and evaluation report, EMC testing with the big help of the Graz University. That's what our location is doing. Now, a final word on this stray field immunity that I touched upon earlier. So why would a system be immune to magnetic stray fields, which is our RF antenna? It's an RF receiver. How can this be better than a magnetic sensor? It's all RF flowing around in the air. How can this be better? Well, think about the AM radio, the classic AM radio. You are tuning your receiver to whatever you would like to hear. So you're only sensitive to the frequency that you attune your receiver to, right? The classic AM radio, well, any radio for that matter. And that's the same thing we are doing here. We are only sensitive in our own transmitted frequency. So if you're operating in 6 megahertz, that's the only one we see. Due to the demodulation and then the low-pass filtering into the baseband. And that's the big difference. These stray fields that we see in the industry, stray fields coming from PWM modulation of brushless motors, you know, the way the motors are excited by PWM fields, and generally by RF fields of all sorts, they are typically in the range of up to 150 kilohertz. Most electric motors today are at the commutation frequency is in the tens of kilohertz range, 10, 20, 50 kilohertz, something like that. A few are going smaller motors into 100 kilohertz. But the norm here measures them up to 150 kilohertz. And the worst, in fact, the worst one is the one at 0. That's where the permanent magnets are. And that's where the magnetic sensor is most sensitive. We have the permanent magnet, and immediately as you place a permanent magnet next to a magnetic sensor, it will give you a signal. And that's the point that's scaring those designers in the automotive industry. Think, for example, you have a gas pedal and you have a cable running next to the gas pedal, a cable that's connecting the battery to the charger or connecting the battery to the drive motor. You have large currents in an electric vehicle, but in any other motor for that matter, large currents generating large magnetic fields disturbing magnetic sensors. Not so the inductive one. So you might say, since I said, well, we're only sensitive to our own frequency, yes. But keep in mind what we talked about earlier, ratiometry. If both sine and cosine are changing in the same way, again, because of the division sine divided by cosine, most of this is cancelled. And overall, as far as electromagnetic compatibility goes, these are a lot easier to design for especially this low frequency stray fields compared to a magnetic sensor. But still, it is after all, yes, it's true. It is a transmitter of 6 megahertz. This is a receiver for 6 megahertz. So yeah, it cannot be taken lightly. So the EMC is an issue on these sensors. That's why we are required to see it in the designs. There are external components needed, filters, capacitors, and things like that to be absolutely safe. And the automotive industry is very cruel in this case. So the limits for maximum radiation or emission are really, really small. So that's I think that's the art of designing such designs. It's not so much about how to design the coil, it's also about how to make it EMC friendly, EMC safe. Electromagnetic compatibility is a big issue there. Now that brings me to the end of my presentation. I hope it was so far understandable. Thanks for your attention.